Hello, my name is a technology in which the
I'm
flue gas.
sorry. I did a mistake. We have to take it from the beginning and again.
We got it. One question. Now that I see it, can I use the pointer because I see here like the mouse, but do we have the option to have another pointer? I think so, right? In pointer
Yes,
option. Yeah,
I
this
saw.
one. Perfect.
Yes,
Perfect. Yeah.
I saw that Raul did that today, no, yesterday. So yes.
Very good. So then we do like that. Hello, my name is Francisco Pérez Calvo. I'm a PhD student at the ETH Zurich. Thanks for following this presentation of the simulation, modeling, and optimization of different seed ammonia-based process configurations for CO2 capture applied to cement plants. The chilled ammonia process is one of the technologies for CO2 capture from cement plants that have been considered within the CENCAP project. The chilled ammonia process is a tail-end capture technology in which the flue gas coming from the cement plant is entering the bottom of the CO2 absorber. The CO2 is captured by means of aqueous ammonia solution, which flows down along the CO2 absorber. The CO2-rich solution is sent to the CO2 desorber for regeneration, and a part of the CO2-rich solution is split, cooled, chilled, and sent to the top of the CO2 absorber in order to limit the ammonia concentration in the CO2-depleted flue gas. Nevertheless, there is the need for a flue gas water wash section in order to further decrease the ammonia concentration in the clean flue gas before being sent to the stack. Additionally, we need a flue gas cooling section, a CO2 water wash in order to purify the CO2 stream before sending the CO2 stream for compression. The chilled ammonia process has been developed and demonstrated for CO2 capture from power plants where the CO2 concentration in the flue gas can range between 4 and 14%. Nevertheless, in the case of the cement plant, the CO2 concentration in the flue gas will be considerably higher, ranging between typically 18% and 22%, and reaching values as high as 35% in volume in the flue gas, depending on the operating mode of the cement plant. Consequently, the scope of this study is to adapt the chilled ammonia process to cement plants for CO2 capture, to prove that the higher CO2 concentration in the flue gas improves the performance of the chilled ammonia process, and to show that the chilled ammonia process has a better performance than MEA-based processes for CO2 capture from cement plants. To do that, we have followed an holistic process development in which we first developed a rate-based model on the grounds of pilot plant tests performed using flue gas specifications typical of the cement plant. With this rate-based model, we perform a model-based process design and development, considering the synthesis of the process, the optimization of the process to minimize the energy consumption, and the integration with the cement plant. The rate-based model of the CO2 absorber has been implemented in Aspen Plus. Here we show a simplification of the CO2 absorption rate as a function of the effective interfacial area, the overall gas side mass transfer coefficient for CO2 transfer, and the driving force. The phase equilibrium is predicted by a Thomson model developed by Kai Thomsen group at the Technical University of Denmark, which not only predicts very well the vapor-liquid equilibrium for the CO2 ammonia water system, but is very good in predicting the solid-liquid equilibrium. Indeed, Thomsen model is able to account for the 5 different solids that can be formed in the CO2 ammonia water system. With this thermodynamic model, we build phase diagrams that we use in order to identify the feasible range of operating conditions of the process at which solids will not be formed. Then transport phenomena are predicted by Rochelle model. These correlations have been obtained for a broad range of structured commercial packings using aqueous solutions which are typical for CO2 capture processes. Finally, the reaction kinetics have been obtained in this work, for which we have performed CO2 absorption pilot plant tests using a commercial structure packing. And the tests have been performed using flue gas specifications of the cement plant, so concentrations of CO2 in the flue gas up to 35% in volume, and using a broad range of concentration of ammonia in the CO2 lean stream, reaching values as high as 17% in weight. This is the test rig that we have used for the pilot plant test of the CO2 absorber. This test rig is located in the technical center of GE at Växjö, Sweden. The packing has a half a meter diameter and 3 meters high. In total, we have performed 82 experimental points for which we have measured the CO2 absorption rate. With the value of the CO2 absorption rate measured experimentally, we fit the parameters, the kinetic parameters of the reaction of CO2 with ammonia to form the carbamate ion, which is the main responsible reaction for the CO2 capture from the flue gas to the liquid phase. Here we show the CO2 absorption rate predicted by the model fitted in this work versus the CO2 absorption rate measured experimentally. We see that the model is able to predict the experimental results within 20% of error in most of the experiments. So once we have a reliable rate-based model that can be applied for a cement plant flue gas conditions, we proceed with the synthesis of the process. The goal here was to move on from the simple flow scheme implemented in Aspen Plus for the power plant application towards the more comprehensive and complete process flow scheme applied to the cement plant. First of all, we proposed some general modifications and improvements of the flow scheme with the goal of decreasing the energy consumption of the process, minimizing the solvent makeup, decreasing the capital cost, meeting the specifications and constraints, and avoiding solid formation. I have to say that these improvements are general to the chilled ammonia process applied to capture from any point source, cement or power plant. These modifications are the solvent recovery section, the recycle of the ammonia and CO2 rich streams to the bottom of the CO2 absorber, the removal of the condenser at the top of the CO2 desorber, the introduction of intercooling stages in the CO2 absorber, the introduction of an acid wash after the ammonia absorber in order to decrease the ammonia concentration in the CO2 depleted flue gas from 200 ppm, leaving the ammonia absorber, to values below 10 ppm at the stack, and the introduction of a direct contact heater, which is integrated for heat exchange with the direct contact cooler of the flue gas in order to reach temperatures of the flue gas at the stack around 45 degrees Celsius and above. Additionally, we have proposed a couple of improvements for the flow sheet, which are specific to the application of the chilled ammonia process to the cement, to the capture of CO2 from the cement plant. The first of them has to be with the SO2 contained in the flue gas coming from the cement plant. Although ammonia doesn't degrade in presence of SO2, if SO2 enters the CO2 absorber, will decrease the CO2 uptake capacity of ammonia, and consequently, we prefer to eliminate all the SO2 before entering the CO2 absorber. Within the CENCAP project, we have performed tests using tests at pilot plant scale, using aqueous ammonia as a solution, and we have been able to decrease the SO2 concentration in the flue gas from 100 ppm to negligible values entering the CO2 absorber. Since the typical SO2 concentration in the flue gas coming from the flue gas will be around 75 ppm, we propose the introduction of an SOx uptake section using aqueous ammonia as a solvent within the direct contact cooler, such a way that we produce as a byproduct ammonium sulfate and obtaining a negligible SO2 concentration in the flue gas entering into the CO2 absorber. Additionally, we have performed tests of the ammonia absorber using flue gas specifications of the cement plant, Here, in the CO2 depleted flue gas, we can expect higher CO2 concentrations in comparison with the application of the cap to the power plant case. We have seen in this pilot plant test that the higher CO2 concentration in the flue gas makes easier the ammonia removal in the ammonia absorber, simplifying the unit operation and shortening the packing. So now that we have the flow sheet for the application of the Chile ammonia process to the cement plant, what we have done is the optimization of the process. In reality, we perform a multivariable sensitivity analysis in which we vary a number of decision variables in the CO2 absorber, the ammonia absorber, and the CO2 desorber in order to minimize the SPECA, which is the specific primary energy consumption for CO2 avoided. The SPECA is a way to consider homogeneously the different types of energy that the Chile ammonia process will need. On the one hand, the steam that is required in the reboilers, and on the other hand, the electricity that is required for chilling, cooling, fans and pumps, and for CO2 compression. And we perform this optimization in order to fulfill certain specifications and constraints which have been defined in the CENCAP common framework. This is, we perform the optimization for CO2 concentration in the flue gas of 18 and 22%, in order to have CO2 capture efficiency above 85%, having ammonia slip in the CO2 depleted flue gas below 200 ppm out of the ammonia absorber and below 110 ppm, at the stack, to fulfill the CO2 specifications for transport by pipeline after the CO2 or compression, and in order to avoid solid formation anywhere within the process. Here we show the results of the optimization. We plot the SPECA versus the CO2 capture efficiency. For the case in which we consider 18% of CO2 in the inlet flue gas, and for the case in which we have 22% of CO2 in the inlet flue gas. Each point in this plot represents one single simulation that converged and that was performed at a different set of operating conditions. In total, we performed around 8,000 simulations. In both cases, we can see a Pareto in which we find that if we increase the CO2 capture efficiency, the minimum specific energy consumption increases. At 90% of CO2 capture efficiency, we see that an increase of 4 points in the CO2 content in the flue gas decreases by approximately 10% the energy consumption of the process. If we extrapolate this finding to a case in which we have a CO2 concentration in the flue gas representative of the power plant case, this is containing 14% of CO2 in the flue gas, we can expect an increase in the energy consumption of 10%. Here we show the same results for the case in which we have 18% of CO2 in the inlet flue gas, plotting the contribution to the SPECA by the chillers versus the contribution to the SPECA by the reboilers of the process. Again, each point represents one simulation performed at different set of operating conditions, and the color code gives the total value of the SPECA. Here we find as well a Pareto in which if we want to decrease the contribution to the SPECA by the reboilers, we'll have to increase the contribution to the SPECA by the chillers. The message from here is the flexibility between different types of energy that the Chile ammonia process has. For the conditions that we have considered in this study, this point is where we obtain the minimum SPECA of the process. Nevertheless, if we change these conditions, we might find this minimum in another point along this Pareto curve. Regarding the overall energy performance, here we show the optimum set of operating conditions of the Chile ammonia process that minimize the specific energy consumption measured as SPECA for the case in which we capture 90% of the CO2 and considering 80% of CO2 in the inlet flue gas. We specify the different energy contributors to the total energy consumption. We see that the main energy contribution of the Chile ammonia process is the steam that we require in the reboilers. In this case, we have assumed that the steam is produced in a natural gas boiler built on site in the cement plant. Comparing to the same case using MEA as solvent, we see that the Chile ammonia process is able to decrease by approximately 45% the energy consumption of the amine-based process. If we compare the Chile ammonia process versus amine-based processes, we see that the complexity of both processes is similar. In this case, we're comparing the flow sheet that we have developed for cement application versus the flow sheet implemented in Boundary Dam for the capture of CO2 from a coal-fired power plant. This similar order of magnitude in terms of the complexity stems from the fact that, on the one hand, the ammonia is more volatile than the amine, but on the other hand, ammonia does not degrade in the presence of impurities, while amines do. Consequently, in the case of the Chile ammonia process, we only have ammonia in the system, while in the case of the amines, we'll have the amine plus tens of degradation products, including ammonia. Additionally, the Chile ammonia process requires very low thermal energy for regeneration. In this study, we have obtained a minimum reboiler duty for a CO2 dissolver of 2.1 megajoules per kilogram of CO2 capture, while for the case of MEA, the value has been 3.8. In the literature, we have found values that can be as low as 2.5. Consequently, the energy competitiveness of the Chile ammonia process is quite good. But this doesn't mean that this brings a much higher packing for a CO2 absorber. For this work, indeed, we have obtained a length of the packing for the Chile ammonia process of 23.5 meters, while in the literature for amines, we find values ranging between 10 and 30 meters. Additionally, ammonia is globally available and has a lower environmental footprint and cost compared to amines. To conclude, we have shown that the Chile ammonia process has a very promising performance with respect to amine-based capture processes for cement application. We have proved that the performance of the Chile ammonia process applied to cement plants improved with respect to the power plant application. We have quantified this improvement, and we have proposed the new process operating conditions using a model-based optimization. And this model-based optimization has been done using a model which has been developed on the grounds of 150 successful pilot plant tests that have been performed at typical cement plant conditions. Finally, new and advanced Chile ammonia process configurations have been implemented. This is all from my part. Thank you very much for your attention. If you have any question or any doubt, I will be happy to reply to your emails that you can send to the email address that you can find at the bottom right of this slide. Thank you very much.